Good morning, everyone. So my name is Volker Roth. I'm from computer science. So today we will start the session with from a viewpoint of computer science, and I will talk about deep latent variable models, which have become very popular in recent years in machine learning. So this is the high-level outline of this talk. So on one hand, we want to go from the chemical space, which is incredibly large, to properties. We want to predict something like energies or forces or electrostatic or dynamics, whatever. So this is what I sometimes call the forward problem. You use a machine learning tool or an interpolation tool in order to predict properties of materials. This is very interesting. We have seen a lot of talks about this yesterday, but what I personally find more interesting is what I call the inverse problem here. So to go back from a desired set of properties to potentially new and interesting materials. And I try to briefly address both directions in this talk. So the forward direction is in machine learning known as the problem of surrogate learning or surrogate machine learning models, where you have some forward model typically implemented by some simulator, whether it's weather forecasting or whatever, and you try to take a shortcut by using a machine learning method. So here I wrote a surrogate machine learning model, but you can replace this by basically any function approximator. So, I mean, as you probably all know, neural networks as well as kernels or Gaussian processes are universal function approximators of smooth functions, so you can plug in anything that you really want here. So, but one additional comment here. So, despite the fact that I have written here machine learning, it's sometimes not even clear if this is a true machine learning model. So, because it's quite frequently in these applications, we can assume that the target is noise-free. And whenever you have a noise-free target, it's a pure interpolation problem. It's not really a learning problem. I mean, there's no overfitting if all your measurements are exactly correct. So, well, this is interesting. Many people have worked on that, but there is another problem which I think is much more challenging, and which addresses much deeper problems in science. So, maybe trying to go back from the properties using a machine learning method, which by definition here must be a generative model, to predict or to create or to sample, how you want to call this, molecules that hopefully are interesting for you. And so this is really difficult because there are big holes in the chemical space. So there are large areas where we don't have any known materials there. So the question is, I mean, to what extent can we solve this extrapolation problem? So to fill these gaps or to investigate if anything is there. Okay, so in order to do that, I will present in this talk a method that combines aspects of generative models. We learned about generative models yesterday in this beautiful talk on approximate Bayesian inference. So basically, it's a generative model that basically here in between it learns a distribution, a joint distribution over molecules and properties. So here, this is a chemical space. So this symbolizes an encoder. So you build a code, a compact representation. In this in this latent space, it's the latent representation of molecules. We add some structure. So you see this. Okay, these dots here. Every dot represents a molecule. Are now arranged in a certain geometric configuration. It's a polyhedron. I will talk about that later. But basically, now we have a decoder, and this decoder basically allows us to sample jointly a molecule and a property. And so the property can be anything you want. So in this case here, the dots in this latent space are color-coded according to the bandgap energy. Okay, so this is where I want to come to at the end of my talk, basically. So, but the overall theme of this talk will be this general encoding-decoding scheme, which has become very, very popular in recent years in machine learning, where you start with something that you want to describe, some domain, and then you have an encoder. Typically nowadays realized it's a neural network, but basically it can also be anything. So anything that somehow compresses, leads to a compressed representation of this space. So this will be the latent space. So it's a compact representation which hopefully allows you to interpret what's going on in this complicated space here. But compactness might also be very important for the second aspect of these models, namely the decoding aspect. So you want to build a generative model that allows you to sample something. So and generative models are typically difficult to set up in high-dimensional, complicated structured spaces, but they might be simple in say, low-dimensional Euclidean latent spaces. And yet the general idea is to compress all the information in this input domain into a low-dimensional latent representation. So this builds a code. This is the encoder, and then we have the decoder. But the decoder does not only decode something, it decodes something under constraints. So the decoder tries to preserve information about something else, and this something else might be whatever you want. In the context of materials, of molecules, it might be properties of these molecules or something. Okay, so a short outline. So I will talk about latent variable models, linear latent variable models. You probably all know about that. Non-linear latent variable models are a bit more interesting, and then I will come back to structuring the chemical space. So latent linear variable models are really simple. So you probably have all seen applications of this kind. So this is an example of a simple clustering or mixture model where you have a latent variable indicating the class membership. So there are two classes, 1 and 2, and in every component you describe your classes with the class conditional density here. So the thing that is latent is this variable z. It comes with this subscript n, so meaning that for any data point you have such a latent variable, and basically this is what you observe. You observe the x. This is your location here, but you don't observe the colors. Basically, the colors are latent, and you want to infer these latent variables typically. So this is an example of a latent variable model. However, a very simple one where the latent variable is just a discrete random variable. So in this case, it just has two components. You can make this story a bit more interesting by assuming that the latent variable is not discrete but continuous, and you basically have the same graphical model here. So I mean, this is just an acyclic, directed acyclic graph, so representing the joint distribution. So a node is a random variable. Now we have this latent random variable, which, however, now is a continuous random variable, and so we have a density here. So P of Z is now, for instance, a normal distribution, and then we express S condition on Z and some further parameters, for instance, also as a normal distribution, where now the mean is a linear function in this latent variable. So basically this means that you somehow have a Gaussian spray can, and you move it along this direction here. This is this direction of this linear function here, and this gives rise to something that is correlated Gaussian. So this is the factor analysis model. So this is one of the most fundamental models in classical machine learning. You can generalize factor analysis or specialize it in several ways. So a specific version of factor analysis is just the classical principal component analysis, where probabilistic version of principal component analysis. But there are also some more interesting generalizations where you have not only one x, but you have now two views on the same data set. You have x and y, so y is just the second view on the same data set. And you might learn now a shared latent representation that explains basically the correlation, the dependency structure between x and y. This is called the canonical correlation analysis model. So if everything is linear, as in this case. So basically, with linear, I mean that the means of these Gaussians are just linear functions of the latent variables. So these are classical models that have been known for decades and studied also for decades in machine learning and in statistics. And there's another great latent variable model, which is called the information bottleneck model, and I will focus a bit on this. The factor analysis model I presented on the previous slides is powerful, but it's still quite limited in that it typically uses only Gaussian distributions, because only for Gaussians we can analytically make all the computations necessary. So the question is there any alternatives? And yes, there was this idea also now 20 years ago by Tali Tishby and co-workers of formulating the problem as a compression and decoder problem, where both compression and decoding uses the mutual information as a cost function. So I guess most of you are familiar with mutual information. So basically, it's just a Kullback-Leibler divergence between the joint distribution of two random variables and, say, their mean field distribution. So where you have the factorized version of that. So in physics, we would call this just the mean field approximation. But just it measures the degree of dependence between the two random variables x and y. And so if x and y are independent, then the mutual information is 0. It's always a non-negative value. So it's quite a nice tool. And so in the information bottleneck, we just use mutual information. We over all conditional distributions of the latent space z given x, we try to minimize the mutual information between z and x, so that is the compression part. You want to compress, you want to lose some information, because compression is a lossy compression. You want to have a compact, approximate representation, but at the same time, you want to keep information about y. So this is this idea of compression on the encoder side and information preservation on the decoder side. The original information bottleneck, however, was not a generative model, so there was no way of drawing samples from this latent space, but in recent years, latent variants of this information bottleneck have been found, and so I mean, remember, this was the canonical correlation analysis picture. You have this shared latent variable that explains the dependency structure between x and y. And now it's for the latent information bottleneck method, it looks very similar. Somehow it's an asymmetric canonical correlation analysis model, where now, again, this latent variable has the property that if you condition on the latent variable, x and y becomes statistically independent, meaning that the latent variable captures all the statistical correlations and dependencies between x and y. Again, there is, of course, a Gaussian variant of that, so that has been studied in 2003 in this paper, and so if you assume that x and y are jointly Gaussian distributed, then, well, basically the equations are not so important. The only important thing is that there's an analytical equation for the mutual informations, and you can basically compute anything you want here analytically, and what you find out is that you basically do canonical correlation analysis, which is not really surprising, because for Gaussian distributions, the mutual information is basically just the absolute value, the scaled absolute value of the correlation. Okay, that's all fine. And this Gaussian IB model is interesting. It might also have this role of a universal latent variable model. It has, I mean, specific versions of it again give you back the CCA model, or the least squares regression model, or the principal component analysis model. So it's really a very, very nice tool for unifying the view on all these different methods. So they can all explain by this basically this graphical model, which just involves this factorization of the joint distribution. So that's fine, but so far everything was Gaussian and linear still. So can we make this a bit more interesting? And yes, it's possible, and this is now the area of nonlinear latent variable models. And so the idea is now to have still something like a Gaussian information bottleneck in the latent representation, but it is flanked from left and right hand side with a nonlinear transformation, for instance, implemented by a deep neural network or whatever. So I don't want to say too much here about neural networks. I think you have had some tutorial talks about that on the first day. I just want to repeat on 2 slides what I think is interesting, and these are some analyses about the expressive power of neural nets, and this goes back to the 1960s, where those people found out that even one hidden layer in a neural network, if it's wide enough, is a universal function approximator for all smooth functions. So in that sense, I mean, this was the first result of this kind, that these networks, these artificial neural networks, are really basically can approximate any smooth function. At that time, however, it was a bit unclear what these functions are. You know, so this basically these functions that occur at these links in this artificial neural network, it was just shown that they exist, but there was no idea how to find them. But then in the late 80s and early 90s, these theorems were generalized. It was shown that you can build universal function approximators from say simple models of artificial neurons. And simple models of artificial neurons typically use simple activation functions, so like the soft plus or like the linear rectifier model. So it's a simple abstraction of a biological neuron built in our computers, and if you equip every node here with such a simple model for an artificial neuron, you can indeed build universal function approximators. So that was all nice, and this has been known now again for decades. But then something happened. Then at some point, people started to think about deep neural architectures, and so to stack more layers on top of each other. And so for many years, however, it was not really understood what was going on there. But then, so starting, I think, with this very nice paper from 2014, there was we got some understanding of why it is good to build deep neural network architectures. And so in that paper, the authors could show that if you have a fixed computational budget, and basically the budget is determined by the number of artificial neurons, the number of nodes in this graph that you have. If you have a fixed budget, then it's much more efficient to place these nodes in many layers instead of having one very wide layer. Although the original theorem tells you that also one wide layer would be enough. However, the complexity, and with complexity I mean the complexity of the functions that you can implement with these networks, it grows exponentially in the number of layers and only polynomially in the width of these layers. So it's much more efficient to arrange these neurons in many layers instead of building very wide layers, as in Gaussian processes. So if you have one layer of infinite width, this is basically a Gaussian process model. Okay, so that's all about neural networks, and now we put everything together, which is we then call the deep information bottleneck. So it's we use these neural networks that so we basically have an encoder network. It can be a deep network, despite the fact that I've drawn just one hidden layer here, and if you have the encoder and the decoder network, and in between we have this bottleneck where we have the compression of the information. And in order to make this a well-defined problem, of course, we have to introduce some parameters. And the overall idea is that, despite the fact that the joint distribution of x and y might be very, very complicated, if x are molecules and y is maybe a mixture of molecules and properties, I mean, what would be a good model for the joint distribution? I simply don't know, but maybe it's much easier to come up with suitable models for the conditional distributions. And for instance, in the deep information bottleneck, we just parameterize the conditional distribution of the latent space given the inputs, and the conditional distribution of the output space given the latent space. So so this we have these parameter vectors phi and theta, which basically parameterize these conditional distributions. And then, well, there's a lot of mathematics ongoing here, but finally you find out that you can re-express these mutual informations that you want to maximize or minimize in terms that you can that you can handle in practice. So basically, on the decoder side, you basically find that this is just a log likelihood expression in the end. Anyway, so what is missing is still this generative aspect, and so in the deep information bottleneck, we assume that this encoder network it models the mean of a Gaussian distribution, but this function here is no longer linear. It's a highly nonlinear function that is represented by this deep encoder network, but now we have a problem. You cannot represent you cannot have stochastic nodes in a neural network and train this network with gradient descent. But you can have stochastic inputs, and this is sometimes known in the literature as the reparameterization trick. But basically, in the end, it's nothing else but the law of how to transform random variables. So basically, you have an external noise input to this network in the latent space, and this allows you to basically to let the gradient flow through the network. That's basically what you want if you want to optimize this by gradient descent. You need a closed form expression for the gradient of all the free parameters with respect to your cost function. And on the output side, you just compare the predictions or those things that you would generate with this generator here with those things that you observe. So this is pretty much the same idea as in approximate Bayesian inference, where you have a generative model and you keep only samples that look similar to those to your observations. Here you do a very similar thing. So you let your generator generate samples, and you tune your parameters such that these generated samples look similar to what you observed. So the only difference here is that instead of sampling, you just optimize the parameters. But the overall picture is the same. You have a generative model, and you try to tune it such that it generates something that looks similar to what you have observed. Okay, so maybe one last word about that. So I mean, the real reason why these nonlinear transformations become very helpful is that in particular, if you implement them with neural networks, is that neural networks are very good at representing structured domains. So for instance, if your input is not just a vector, but a graph, a labeled graph, as for instance, a molecule, or if it's text or whatever. So neural networks are so flexible that it's very, very easy to handle structured inputs and also structured outputs. So also the output could be structured, it could be a small string, having some grammar, and I will present some examples of that, where the generator produces syntactically correct small strings, and so this is really the I think I mean nonlinearity is nice, but the real advantage of these networks is their flexibility, in that you can easily handle structured data. Okay, so let's come to the. I mean, after these few slides about say the machine learning and neural networks, let's come to our problem. Let's come back to what we want to do. We want to find structure in the chemical space, and basically at the very end we want to address this inverse problem. And how can we do that? So I mean, this is just we've seen this slide already at the beginning. So just a reminder, what we want to do is to use some machine learning tool and to build some generative models that allow us to sample molecules, to draw new molecules together with properties. Or maybe a slight variation of this theme would be to fix the desired properties that you're interested in, and then you want to draw all the molecules that have these properties. Seems to be complicated. In particular, this problem is so complicated because the chemical space is so diverse. So, you know, it's not so clear to what extent we can really capture all the structural variations of molecules with a simple, say, low-dimensional latent representation. Okay, so you've already seen this slide at the beginning again. So this is now one attempt to do that. So so every dot here is a point in a three-dimensional space, but of course 3 is just chosen here in order to be able to visualize it. But basically, what this encoder network does, it takes on input a graph representing a molecule, and it maps this graph to a point in 3D. And there is some additional structure. You see that there are some extreme points here, which we call archetypal molecules, and in these applications they have been tuned such that they are extreme with respect to, for instance, here the band gap energy, which was the desired property in this application. And then we have acting on this latent representation. There is a generator. It's now a generative model that allows you, or that associates with every position in this three-dimensional space a new molecule and a desired property, for instance, here, a band gap value. So you basically really learn the joint distribution of molecules and properties. Okay, so this is of course in principle a classical model in machine learning. It comes under many names. It's very similar to variation autoencoders, or we call it information bottlenecks, because we have it's not really an autoencoder you have on the decoder side. You might have something that is different from the encoder side. But anyway, so it's just you have this encoder decoder architectures. But there is a problem with all these approaches. So and the problem is that you are lacking a global structure in the latent space. So in the latent space, in the classical models, points are only coupled locally. So you add some noise in the latent space, and this leads to a local coupling of all your dots in the latent space. So what you can be sure that something that is close by in the latent space is also close by in the output space. But you cannot be sure that something which is far away in the latent space is also far away in the output space. It can also be close. Because there is no global coupling in the between all these points in latent space, so they're just coupled locally, and I think this is a very strong problem in all these models when it comes to interpreting the latent spaces, because I mean we try to visualize these latent spaces and we try to make sense out of them, but you always have to be aware that I mean the placement of these points only locally makes sense, so there is no global structure in these latent spaces typically. So the idea was to add some global structure, and this brings me to the last topic I want to discuss here, this idea of archetypes or archetypal molecules. So it's an idea that comes from biology, a few words about this later. But the idea, first technically, is that you add some structure in the latent space. You no longer have an arbitrary placement of your points in your latent space, but you define some extreme points, and all the other points must be convex mixtures of these extreme points. So every dot in this latent space representing a molecule is now a convex mixture of other molecules. These are these archetypal molecules, so let's see how we can make sense out of that. So this goes back to a very nice paper by Uri Alon's group. That was published in Science in 2012, and they came up with a very nice theory about evolution and optimality and the geometry of phenotype space. And basically, their idea is as follows: well, in a biological system, I mean, a phenotype might be defined as a vector of traits, which is just some quantitative measurements, and the space of all the phenotypes is known as the morphospace. And what they try to explain in their paper is the connection between these principles of natural selection, where basically you have to optimize some fitness function, and say these some fundamental properties of the geometry of the morphospace. The point here is that organisms need to perform multiple tasks, and all these tasks contribute to their fitness. And so it's a multi-objective optimization problem, and as we know from optimization theory, solutions of multi-objective optimization problems live on the Pareto front, and so which characterizes the best trade-offs between the different requirements in these different tasks. And so what it means here is that if on the x-axis you have the task 1 performance, and on y-axis you have task 2 performance, then there's a Pareto front of optimal solutions which somehow have the highest fitness. And if you replot the same situation by now exchanging the axis, by having now the trait 1 on x and the trait 2 on the vertical axis, now you might have the following situation. Assume that this is one species that is optimal for task 1 performance, and this is optimal for task 2. And now look at, I mean, in principle, this space could be populated everywhere. You could have species placed everywhere. But assume you have a species here, then it has greater distance to both this and this compared to this one. But greater distance to this extreme species means that you have reduced fitness. So evolution will drive all these species which might have initially lived here towards this connecting line that somehow connects these two archetypes, these two extreme points. And this is really what is observed in biology. It was a question of centuries. Why is the morphospace so empty? I mean, there are many species, but basically the space of all possible configurations is empty, almost empty. So the species live on tiny submanifolds of this space. And this is an example with where you have the molar teeth of rodents, and you see, okay, in principle, so basically you could have any sizes or size ratios of these molar teeth, but what you observe is that basically all the observations lie on a line, and if you look at the extreme points, you find here those rodents that eat only plants, and here those that eat other animals, and those that eat both are somehow just a linear interpolation of these extremes. And the cruel thing, the interesting thing is that everything else is empty. So there is no species living here. And if you look at that and think about it for a while, this looks a bit like the chemical space. It also seems to be empty in large areas. So the idea was, despite the fact that there might be not a one-to-one translation of these concepts to chemistry, it might still be a useful tool for studying, say, the structure of molecules. And so, but of course, in order to do that, you have to come up with a mathematical model. And to my knowledge, the first paper addressing, say, the statistical aspects of this archetype problem was addressed by Keller and Bremen in this paper from '94, where they reformulated this as an optimization problem, where basically you have an alternating maximization. You first require that the observations are convex mixtures of the archetypes. So every blue dot here, what you observe, must be a convex mixture of these extreme points. But at the same time, you require that these extreme points are convex mixtures of the blue dots, basically in order to avoid trivial solutions, because otherwise you could shrink all the blue dots towards the center of the space, and then this constraint would no longer be active. So it's a complicated alternating optimization problem, what they formulated in these papers. But the take-home message is that these archetypes, or the polygon connecting these archetypes, can be seen as a statistical description approximation of the convex hull of the data. Okay, so one problem with the original archetype model was that if you go back to this plot here, you have to find the right space in which you have this nice, say, convex mixtures. And here it was the size ratio of two molar teeth. But why the size ratio? I mean, here we had maybe the authors claim that this is natural because you want to normalize with respect to the total size of these animals, of the species. But it's not so clear in most applications what is the right space to plot this and to see these convex mixtures. And the idea was now to somehow let the network decide what the right space is, and to have this archetypal construction here with these extreme points in the latent space, and we have again these flanking networks that somehow automatically find a nonlinear transformation, such that you can reason in a reasonable way represent all these observations as convex mixtures of these extreme points. So this is basically the same model as before, however with this slight twist that now you have introduced a global coupling in the latent space. So that the points are not placed arbitrarily somehow in the latent space. They are coupled globally in that every point here is a convex mixture of the extreme points. And if these are molecules, then these are extreme molecules. But now the question is, what makes them extreme? Of course, that depends on what your output space is. If your output space is now the joint space of molecules and a certain property, then these will be molecules that are extreme with respect to this specific property that you are interested in. And this is what we see here. So this is basically such a space. It's just a polyhedron here now with 4 archetypal molecules in this case. And on the output space, we have the molecules themselves, here represented as Smyth strings, together with a property, which in this case was the bandgap energy. And what you find then is that automatically these networks, these flanking networks, learn transformations of the chemical space such that molecules with high bandgap energy are arranged close to this archetype, and those with a very low bandgap energy are arranged here, and then you have some other archetypes representing some structural variations of all the other molecules. So if you now think that this is interesting, well, it is, but there is a huge problem here. So, and the problem is that, okay, I skip that. The problem is that many molecules have roughly the same bandgap energy. So this is, in a sense, a a many-to-one map. But so at the positions of the archetypes, you would have to represent many structural variants of molecules with a certain bandgap energy. But at this vertex points of this polyhedron, there's simply not enough space to represent all these molecules, all these structural variants of these molecules there. So you have to do something else. And the idea then was to have another, say, orthogonal space in that in this subspace you have some further degrees of freedom, some further coordinates in your latent representation. However, you have the explicit requirement that these points here, so any coordinates in these points should have no mutual information with respect to your property. And you see this here all these colors are scattered all over the space. So coordinates here are forced to have no information about the bandgap energy. And now this is now really what you want. You have on one hand side you have this low-dimensional representation with these extreme molecules representing extreme cases with respect to your desired target property. And on the other hand, you have another orthogonal space that captures all the structural variations. So if you fix a point here and you sample from this space, you will sample all the molecules that have more or less the same bandgap energy. But this is now really a great tool, because now you can explore, you can fix, for instance, a desired range of your output property, and now you can use your generative model. You can sample from that space, and this gives you an overview of what the model thinks are useful structural or are valid structural variants of molecules all sharing this desired properties that you're interested in. So some details here. So we use technically we basically we represent molecules as a combination of SMI strings and 3D descriptors. And this is in particular important on the decoder side, because generating new molecules based on 3D descriptors sometimes is difficult. It's sometimes difficult to really find out what molecule it is in the end, because these descriptors might not be so easy to interpret. But if you jointly always generate the SMI strings, then you already know pretty much what molecule it is. And so we use a specific version of a SMICE decoder that has been presented last year, where it's a specific decoder with a built-in SMICE grammar parser. So you basically constrain your decoder to generate only syntactically correct SMICE strings. So and now of course, now you can play around with this model. Now you can visualize all these molecules that, for instance, have high bandgap energy with indicated in these bluish colors, or a low bandgap energy, and you can explore the structural variations of molecules sharing this property and do all these interesting things. And one question we are addressing currently together with the group of Anatol von Liedefeld in Basel, our collaborators, questions like, how complete are all these commonly used data sets like the QM9? So are there any molecules that could be there but are not in this database? And what properties would they have? And so now you can try to address these problems. You can now sample molecules from this generative model, and you can there are first indications that there are indeed some interesting molecules that. Okay, but details about that will appear elsewhere. Okay, so let me wrap up. So the chemical space gives rise to a huge variety of challenging machine learning problems, and our approach was to somehow to focus on visualization, on finding structure finding a structured representation of this chemical space that might allow you to address this inverse problem in a specific way. And I hope I could convince you that these deep information bottleneck models are really very powerful tools for doing that. They are generative in nature. You can sample from these models, but then to be honest, there are many open questions. It's still not so clear what can we do in these areas of the chemical space which are just empty. So even these models are not great extrapolators. So okay, good. With that, I would like to thank you for your attention.
Very much, Volker, for the very nice talk. So we are open for questions. There's one. So I throw it from mid-distance.
Thanks for this fantastic talk. How easy it is to probe many different properties? Do you need many different generative models to sample these multivariate?
No, this is a very good question. So I presented here only examples with one property, but the model is absolutely general. You can plug in all your properties that you're interested in. So whatever you, I mean, it's up to you what you choose as the property. There's no reason that this is just one property. You can all, I mean, this was very experiments on QM9. You can use all these 12 properties there. So there's no, I mean, it's interesting to observe, say, the required dimensionality in this orthogonal space. Of course, the more properties you use here, the more bijective this mapping becomes, and you need lower and lower dimensionalities here in this orthogonal space. So this is also a very interesting observation.
So could you say more about this orthogonal space? Is this also encoded by the autoencoder when you train it, or is it constructed somehow?
Yes, basically it's just you just have a model for two disjoint subspaces in your latent space, and you have an additional term in your loss function where you try to minimize the mutual information between this space and the target space. This seems to be somehow like something like a trivial extension of this autoencoder scheme, but it turns out technically that this is difficult to do. So maximizing mutual information is quite simple, but minimizing them is technically difficult.
Great talk. So I was wondering, so when you do these embeddings in these orthogonal spaces, have you tried to see if there are, for instance, if you leave some of your structures out from QM9, whether that lie in between extreme points, whether you can actually predict their position accurately, and whether their position is in the thing or the position where you would expect them to be, had you also included them in the training. So sort of like as a cross-validation, whether you can predict their position based upon their properties.
Yeah, we ran a lot of cross-validation experiments, of course, and yes, I mean you see here that, I mean this is basically what you see here color-coded is actually the performance on a holdout test set. So we trained the model, and we then predicted, or we then fed this holdout test set through the encoder, and then so the encoder maps all these points which are not part of a training set into this latent space, and here we just color coded with the desired property, and you see that they nicely arrange as you would expect. So yes, but of course you have to do all the statistical validation of these models.
And maybe I also have a quick question. So if you think about that you have different latent spaces for different properties, maybe, and then you may know essentially physical relations between the properties, which would imply relations between different latent spaces. So could you construct kind of an ensemble of latent spaces where you encode physical knowledge?
Yeah, I think this is a very interesting direction to go to. So, I mean, you already see the idea coming up here. So you have already here a division into two latent spaces, and they should behave differently with respect to the properties that you're interested in. Of course, you can now substitute this with a whole bunch of properties and have somehow statistically related latent spaces, but I mean, of course, it's not so clear how you would express these relationships, but you might still have, or something that comes to my mind would be just some additional, say, functions implemented by networks that somehow relate these latent spaces, and you can put some further constraints between these latent spaces.
All right, so I see no more questions. So let's thank Volker again.